Go ahead.
Okay, so welcome everyone to the Technion Robotics Seminar. I am as excited as can be to have Kiril Solovey, who is a postdoc, a friend, and a colleague, to tell us about the work that he's been doing in the past few years on mobility on demand systems. Kiril is gonna define the whole problem. Kiril is a phenomenal researcher with, I think, almost as many best paper awards or finalists as fingers as I have in one hand, which is more than a lot achieved in a lifetime. He's a Fulbright postdoctoral scholar, and his PhD was funded by the CLORS Scholars Program. He did his first postdoc at Stanford University. And as I said, now we're glad to have him here at the Technion. And with that, I'm excited to pass the virtual stage to Kiril.
Thanks, Oren. You're very kind. I'll mention a few of our papers together in this talk as well. So hi, everyone. I'm very excited to be there with you virtually. I think that my title is quite self-explanatory, but I'll make sure that you will understand all the details. So I'm going to talk about multi-robot systems. These are applications where we have multiple robots that work together to accomplish some joint tasks. And there are quite a lot of fascinating problems, fundamental problems about those systems. And I will try to expose you to those as well. And in addition to that, I will also focus on applications of multi-robot systems in smart mobility. For instance, how to orchestrate an entire fleet of autonomous vehicles that need to drive people around. So with that, I'll start the talk. And of course, if you have any questions, please feel free to jump in. So there are numerous applications that are already using multi-robot systems nowadays. One of the most common examples for that is what's happening in Amazon warehouses. So every time you click the Buy Now button on Amazon, you're commanding a fleet of those Kiva robots to move shelves around in a warehouse facility. And there are many more companies that have similar technologies. In parallel, there is quite a lot of interest, both in academia as well as in industry, in using fleets of drones, especially for package delivery. So Amazon has already a branch that is focused on that, and there are many more companies. Now, why should we use multiple robots in the first place? Of course, unlike, in some tasks, we could have one very complicated robot that would accomplish this given task, but in many cases, we can get much more efficient and reduce the cost significantly if we use multiple robots that are quite simple, they are inexpensive, and they're easy to operate as well. So multi-robot systems can give us a lot of efficiency that we cannot get with humans or single robot systems. Now, to me, the most exciting application of multi-robot systems would happen in a few years from now. In smart mobility, we already have autonomous vehicles with certain levels of autonomy already driving on our roads. And even in Israel, we have some versions of autonomy embedded into our vehicles already. And it won't take long before we'll have entire systems of autonomous vehicles that would roam our roads. And nowadays, most of the research on autonomous driving is focused on the sides of perception and planning not planning, but a prediction actually. And the reason there is a lot of research about it is we want to get our systems to be as safe as possible. But if we really want to push how safe those autonomous vehicles can get, we need to start and work and understand how to reason about the interactions of those systems, one with another, autonomous cars interacting with human drivers around it and interacting with pedestrians around it. Now, in addition to safety, there are many benefits that we can get from autonomous vehicles and smart mobility systems in general when we start to understand and reason about those systems from a global perspective. And we can then optimize how we drive our vehicles in the most efficient way to minimize traffic congestions and even account for societal issues such as fairness and accessibility. And I hope I'll expose you to some of those issues later in this talk. So multi-robot systems hold a lot of promise in them, but to reap all of those rewards that they promise, we need to face and account for very hard optimization and algorithmic challenges that they provide, that they give rise to. So why are those problems hard? And I'll expose you throughout this talk to some of those difficult problems. For now, I just want to give you a taste of why are those problems hard. So first of all, we have robots operating in the physical world. Each such robot has several degrees of freedom. It has complex constraints on the dynamics. And moreover, we also need to account for interactions between multiple robots. So this gives rise to a very high dimensional search space, which is already hard to reason about. Now, if we start to deploy those systems in the real world, we also need to model their interaction with society, with the environment, with people around it, and so on. And we also need to do it in a much greater scale. So imagine reasoning about the entire system of vehicles operating across Haifa or San Francisco. Now, the last challenge is that we want to be able to design algorithms that have strong theoretical guarantees, because we want to ensure that they are correct and they are as efficient as we can get them. So we want to ensure that the running times of them are bounded. Why? Because we want to be able to replan efficiently if there's something unexpected happening in the environment. We want to make sure that the solution quality is high and, of course, safe. So all of those considerations introduce very hard optimization and algorithmic challenges that we need to account for. So in response to that, my research leverages ideas between the areas of optimization, engineering, and transportation sciences to develop effective control and decision-making algorithms for multi-robot systems. And today I want to expose you to what are the interesting problems in this domain and where I believe this domain is going to go to in the future. So this talk will have two parts. In the first part, I will discuss some fundamental aspects in multi-robot systems, namely motion planning, task allocation. And the second part of the talk, I will discuss the applications of multi-robot systems within smart mobility. So with that, we can start with the fundamentals part. So the most basic problem that comes to mind when we're discussing multi-robot systems seems to be motion planning. So in motion planning, we're given a set of start locations for each robot and a target location for each robot. And our goal is to find collision-free paths that move simultaneously the robot from their start positions to the target positions, while of course avoiding collisions with the environment as well as one another. Now, this is a problem that is common in any type of system that operates multiple robots. And unfortunately, it's very hard to solve practically. And already in the example that I'm showing you right now, this is a hard problem. So if we're thinking about it from the perspective of computational complexity, even when our robots are disks, they're translating in the plane amid polygonal obstacles. This is already a piecewise hard problem. And the reason why those problems are hard is because in many cases, it's unavoidable to reason about them from a very high dimensional search space, which combines the different configurations of all the multiple robots we have to get working together. Otherwise, we cannot just solve the problem. It's in many cases, it's insufficient to look at the problem for a lower dimensional search space that just captures the configuration space of a single robot. So this is a very challenging problem, but in many cases we can reason about its structure and extract some interesting properties that we can exploit in efficient algorithmic solutions. And I want to walk you through some such approaches. So I started working on multi-robot motion planning, where I just started my master's degree. I was working with Dan Halperin from Tel Aviv University. And what I observed together with Danny was that there is quite a lot of similarity between the multi-robot motion planning problem that we have on the left, which is reasoning about robots operating in some continuous three-dimensional space, and puzzle-like problems that we have on the right. So on the right, we have an example of a 15 puzzle. I'm sure that many of you are familiar with. The goal in this puzzle is to shift tiles around until they are rearranged in the right order. And you can think about generalizations of these puzzles to graphs and so on. And this is a discrete problem on the right, which has rather efficient algorithmic solutions that can solve it if we compare it to the continuous space we're coming from in multi-robot motion planning. However, it turns out that there is quite a lot of structure or similarity that we can exploit between those two seemingly different problems. So in particular, in a series of papers together with our collaborators, we show that in many cases, we can transform the multi-robot motion planning problem into a sequence of those puzzle-like problems. We can solve those puzzle problems efficiently, and then we can transform this discrete solution into a continuous solution, which will be collision-free and in many cases even near optimal. So we can show that for some problem instances, we have polynomial time guarantees using such an approach, as well as even optimality guarantees. And this led to the development of some of the most efficient algorithms we have today for multi-robot motion planning. In terms of scalability, they can cope with very large numbers of robots. And to develop those approaches, we leverage techniques from computational geometry. Now, with that said, there is still big limitations of those kinds of algorithms in that they are currently only applicable to mobile robot systems operating in two-dimensional space. We still don't know how to extend such approaches for more complicated robotic systems. So I faced this when I worked on those kinds of algorithms. I understood that I have to look somewhere else to be able to design more general approaches for multi-robot motion planning that can cope with more complicated robotic systems. And so to do that, I understood that I need to understand better how do we reason about motion planning tasks for single robot systems that can be very complicated. So for example, a manipulator arm, an autonomous vehicle, or even a spacecraft. How do we plan the motion of those complicated robotic systems? And I turned to study sampling-based planners. So in this slide, I want to focus on what are sampling-based planners for a single robot system. And then I will give you some insights into how to extend them efficiently to multi-robot systems. So if we are thinking even on the setting of motion planning for a single robot, so imagine you just have one robotic arm or manipulator operating in an environment with obstacles, this problem in itself, without other robots working together, can already be hard, computationally hard. And again, the reason for that is that the search space in this problem, or the configuration space that it introduces, has high dimension. And so if we want to explicitly construct the set of all configurations in which the robot is collision-free with respect to the environment, it can take a lot of time computationally. It's just computationally very difficult. So there is a set of very promising approaches for motion planning that overcome this limitation by aiming to capture the structure of this configuration space rather than implicitly through sampling. So how do those sampling-based approaches work? They have the following shared structure, which differs slightly more or less between the different approaches, but it more or less works in the following way. We can sample a bunch of configurations for a robot. For each such configuration, for each sample configuration, we can ask, is it a colliding configuration or not? And we can answer such a question, local question, very efficiently, because all we need to do now to answer this question is to take the three-dimensional model of our robotic system and overlay it with some representation of the obstacles in the environment and ask, is this in a colliding configuration or not? And we can do it very efficiently through collision detection. So this is a tool we have from graphics. So now that we have a set of non-colliding configurations, we can draw very simple connections between nearby configurations. So imagine walking along the straight line path between one configuration and the next. So now using those simple connections, they can represent edges in a graph. So together with those configurations and edges, we are forming a graph structure that has the following very useful property. A path on this graph that connects one robot configuration to another also represents a collision-free path for our actual robotic system that lives in the high-dimensional configuration space, as well as in the environment in which it operates. So, and what is very useful or very appealing to us in those sampling-based planners is because of those simple building blocks that are necessary to implement them, we can apply those techniques for virtually any robotic system. Okay, because all we need to do now is to be able to validate that a certain configuration is collision-free or not, and we need to be able to make connections between nearby configurations. So together with my collaborators, including Kostas Bekris, Michal Kleinbot, Matthew Tsao, and others, we push the boundaries in terms of what kind of problems we can solve with sampling-based planners, how complicated of robotic systems we can deal with, and how many degrees of freedom they can have in practice, and how efficiently we can solve those problems as well. In addition to that, we laid strong theoretical foundation to analyzing those sampling-based planners. And today we have quite a good understanding of how to reason about questions of the flavor. How many samples do we actually need to draw? Where do we place those samples? How do we draw the connections? And what is the quality of the solution that we can get from such methods? So armed with this understanding of sampling-based planners for single robot systems, we turn to study and design planners aimed specifically for multi-robot systems. So now imagine that you have just a simple system that consists of just two robotic manipulator arms that work in the same environment. So given that you saw the previous slide and you are familiar with sampling-based planners for single robot systems, the first thought that comes to mind is, why can't we just apply sampling-based planners as they are on multi-robot systems by thinking about those multi-robot systems as if they were just one single, although quite complex, robot? So such an approach works in theory, but in practice, it doesn't work well. It simply fails very quickly because of the high dimension of the search space that we have in the multi-robot case. With that said, in multi-robot motion planning, we have quite a lot of structure that we can exploit in the development of approaches that are scalable for multiple robots. And for example, the approach that I'm going to describe next can cope with as much as 10 robots working simultaneously, where each robot has as much as 66 degrees of freedom. And this line of work has been it's been done in collaboration with Florian Zaltzman, Raoul Shom, and others. And I want to walk you through one such approach called a DRRT. So imagine again that we have this simple setting of just two robots working simultaneously. The first thing that we can do, we can get quite a lot of information already just by constructing for each individual robot its own sampling-based graph. So imagine for each robot, we're constructing its own sampling-based graph, where each such graph captures the structure of this specific robot configuration space. However, what this graph doesn't take into consideration, those smaller graphs, is the interaction between the two robots working simultaneously. So to account for the interaction, we can reason about it from another graph structure called a tensor graph, which is the graph that appears on the right. So what is this tensor graph? It is simply a tensor product between the two smaller graphs that we have in the middle. So what does the tensor graph mean? Let's take, for instance, one vertex from this tensor graph. So imagine you have the start vertex in the tensor graph. All it represents is a combination of two configurations, the start configuration of the first robot and the start configuration of the second robot. An edge in the tensor graph, so the red edge that I have depicted here represents two edges, so a combination of two edges, one for the first robot and one for the second robot. And what does it mean physically in the real world? Well, when we're thinking about how does this edge transfer to a motion of the robot, all it means is that the two robots work simultaneously, each one along its corresponding edge in the configuration space. And so the tensor graph has a lot of useful structure that we can exploit. In particular, even though it was constructed from the single robot graphs. So in particular, if we get rid of all the edges in the tensor graph in which two robots are colliding with one another, and we search for a path along this tensor graph from the start vertex to the target vertex, we are guaranteed to have a solution, a collision-free solution for the multi-robot problem in which the robots do not collide with obstacles or collide with one another. So we're constructing those single robot graphs, and by combining them through this tensor product, we can get a more complicated graph that also encodes the interactions between the multiple robots, which of course is useful, but in itself is not enough. And why? The tensor graph on the right is very computationally intensive to construct. Its size is exponential in the number of robots that we have in our system. So it might be scalable enough to cope with 2 robots, but not with 10. So we want to somehow exploit the rich structure that the tensor graph provides, but make it in an efficient, computationally efficient way. So the approach that we came up with, instead of constructing an explicit representation of the tensor graph, it constructs implicitly only the edges or the vertices that are necessary to uncover a solution. So actually, it doesn't uncover only the path itself, it also uncovers additional edges, but it does so in a very minimalistic manner so that we can uncover this path in the tensor graph quite efficiently. And I want to walk you through some of the details of this approach. And again, the idea that we're exploiting here is we're using a sampling in the multi-robot space to uncover the portions of the graph that are useful for finding a solution here. So I want to describe to you how do those iterations work of the algorithm. We're assembling a random configuration, but now this configuration lies in the multi-robot space. And then we ask, what is the vertex of the tensor graph that we have explored so far, which is the nearest to this random sample. As we just started running this algorithm, it will be just the start vertex. So the start vertex is also the nearest vertex. And then we ask, from all the edges, all the neighbors of the start vertex in the tensor graph, which one is in the direction of the random sample? So this would be this red edge. And it turns out that these simple primitives that I just described, we can implement them without explicitly constructing the tensor graph. We only need to rely on the single robot graphs that we have in the middle of this slide. And this is one of the reasons that we can implement all of those steps efficiently and eventually find a solution quite quickly. So now that we identify this edge, we need to verify whether two robots are colliding while moving along this edge, which we can do quite efficiently. We know how to solve collision detection very well. And so we add this edge to the graph, and we repeat this process again and again. So I want to give you another example. So imagine that you already uncovered this black portion of the tensor graph. So now again, we sample a random point in this multi-robot space. We ask, what is the nearest vertex of this tensor graph that we explored so far? And then we add the edge from the nearest vertex that is the most in the direction of the random sample. And in this specific case, we reach the target. So we repeat this process until we reach the target. And what we can prove mathematically and theoretically about this algorithm is that we eventually can converge to a solution while we rely on the number of samples that we draw. So once we sample enough of those samples or do enough of those steps of the algorithm, we will eventually uncover a solution. And moreover, we also have theoretical results that tell us how to construct the single robot graphs such that the solution that we find on the tensor graph will be close enough in terms of solution quality to the optimal solution to the problem. But most importantly, after incorporating some heuristics to such an approach, we can solve quite large problem instances that involve as much as 10 robots. Now, so far, we've only focused on one very fundamental aspect of multi-robot systems, which is motion planning. Of course, this is just, you can imagine that there are many more building blocks that are necessary when we want to actually deploy those systems in the real world. And one such building block is task allocation. So in task allocation, we're also interested in not necessarily what is the path that we're taking, but also who does what. So imagine in the example that we have on the left, where we have to rearrange a set of blocks using our multiple robots, how do we know a priori which robot moves which block? This is what the task allocation mechanism is going to tell us. And we explored those kinds of questions in settings related to from robotic manipulation to even distributing fleets of satellites for gathering information on the surface of Mars. And although I cannot say that there is one approach that is applicable to all instances of task allocation, multi-robot task allocation, in many cases, there is some underlying structure that we can exploit in those task allocation instances so that we can design effective algorithmic approaches to tackle those problems. So for example, in this satellite information gathering mission, this problem can be in fact represented as some scheduling problem using heterogeneous agents, and for which we can design a polynomial time two-factor approximation algorithm using flow-based approaches. So now I would like to wrap up this part with some interesting future questions that I believe will be important to tackle in the next few years. Although we know how to solve quite efficiently multi-robot motion planning as well as task allocation problems, we don't know how to combine those two problems together. So we don't know how to solve motion planning while simultaneously optimizing for the task allocation. And it will be interesting to exploit ways to merge those problems together and to solve them simultaneously. Now, in addition to that, with all the progress that we've made in multi-robot motion planning, we're still limited in the number of robots that we can cope with at a given time. And I think that using the power of machine learning, we might be able to overcome in some way the curse of dimensionality, or at least alleviate it. So it will be interesting to explore in the future how we can use learning-based approaches that would tell us or help us to understand what are the interesting or useful places in the multi-robot problem that we need to sample, or where should the search lead, or how do we altogether reduce the dimensionality of those problems. There are a lot of interesting questions in the intersection of multi-robot motion planning and autonomous driving that I hope to explore in the future as well. For example, this is what we have on the left. What is the best way to route vehicles through a given road segment? We know that we, as human drivers, we have some rules that we need to abide, but it's unclear whether those rules, or it's actually quite clear that those rules are not necessarily leading to the most efficient solution that autonomous vehicles can execute. So the question I'm posing here is, how do we leverage those motion planning algorithms we already have to understand what is the best way to route autonomous vehicles through a given local road segment? There are also quite a lot of fascinating problems in the intersection of motion planning and game theory. In the future, I want to understand how we can reason about the interaction of multiple vehicles or multiple players that we have on our road. So imagine a setting of autonomous racing where we have each autonomous vehicle has its own objective, and we want to find the path for our vehicle that interacts or accounts for the interaction to the other vehicle. And so it is, in such a case, it's not enough just to optimize its own path. We need to account for how the behavior of the other driver evolves with respect to ourselves. And so I believe to tackle those questions, we need to integrate into our motion planning algorithm some constraints from game theory, for instance, converging towards some version of an equilibrium. And once we get a good handle about autonomous racing, we might also be able to reason about more complicated problems involving autonomous vehicles driving around humans whose objectives might not be known a priori. So, of course, autonomous driving poses a lot of interesting questions in this domain. And now I want to take you to think about those questions from an even broader perspective. So this wraps up the first part of the talk where we discuss the fundamentals of multi-robot systems, and we're moving to discuss the applications of those systems in smart mobility. So in the future, we might be able to control all the vehicles that we have on our roads. And so our goal is to push the boundaries with respect to how many vehicles we can reason about at a given time by building on the approaches that we already have to control each individual vehicle. With that said, I want to also clarify, I want to be realistic, and it might not be possible to reason about those problems with the same level of details that we're thinking about them when we're just have a small system of robots, 10 or 20 working together. So now I want to take a slightly more abstract but a higher level perspective that will allow us to reason about those large-scale autonomous vehicle systems. And just to connect the two parts, once we will get a solution from this high-level perspective, which tells that each vehicle what is the specific road that it takes and where it takes the different turns, then we can execute those solutions in a more localized manner using the coordination approaches that we already have. So the most fundamental problem that I want to describe to you in this domain of operating smart mobility systems is called autonomous mobility on demand routing, A-mode routing. So imagine that you have a fleet of autonomous vehicles operating over an entire city. And the question is, what is the best way to use this system to drive people around? Okay, so in addition to the road network that in this case is represented by a graph, we also have some characterization of demand, that is the number of people that are going between every pair of origin and destination vertices. And what we want to find is routes that specify for each vehicle what are the routes that it takes to drive the passengers. So you have this vehicle here, as well as what are the routes that the empty vehicles should take, and what are the next passengers that they're going to pick up. Now, what is the objective? How do we want to optimize this system? Considering that we assume here a centralized perspective in which we operate all the vehicles that we have in our system, we can strive now to optimize for global objectives. And the specific objective that we want to optimize in this case is minimizing the total travel time of all the vehicles we have on our road. Now, to do that, we need to account for the effects that the individual vehicles have on the travel times of the other vehicles on the road. And so we want to account for congestion effects that are introduced by the system itself. So our approach needs to be congestion aware. So here I want to mention that there has been quite a lot of research on those kinds of questions in the last 10 years. However, most of the approaches that have been developed for this kind of problem are usually formulating it as some version of a mathematical program, and which is then solved by a solver like a Gurobi or Simplex, which in itself is useful, but it's not scalable enough, and it cannot deal with large scenarios involving thousands of vehicles operating over entire cities. In a recent work together with Mauro Salazar and Marco Pavone, we showed that actually this specific problem has a useful structure that we can exploit in the design of a very effective algorithmic approach. And so we can deal with this approach doesn't only have nice theoretical properties, that is, it returns the optimal solution to our congestion-aware A-mode problem, but it also can tackle very large problem instances very quickly. For example, we can plan the entire rush hour demand traffic of Manhattan in just a few seconds on a commodity laptop. And so now I want to walk you through the details of this approach. Now, maybe before we jump into the algorithmic details, one part that is still missing here for you to understand what is the problem that we're solving is how do we model congestions. Here we're taking a very simple approach that is also commonly used in transportation literature, as well as in algorithmic game theory where they're studying congestion games. So we are assigning to every edge in our graph a travel time function, which simply tells us how does the travel time evolve with respect to the number of vehicles? Okay, so it's a very natural thing to do. Now, this is such a way to model traffic congestion or vehicle traffic flow is quite simple, and it also leads to relatively simple computational models, but it does have its own limitations, and I will talk about it later in a few slides from now. So we have this model, and now we are ready to describe the problem formulation. So we can represent this A-mode routing problem as a convex program. Again, mathematically it's useful, but in itself it's not enough, because if we just throw this problem into a convex solver, it won't be scalable enough for us. But just to give you a concrete definition of the problem, the objective function here is convex. It is minimizing the total travel time of all the vehicles on the road, where for every edge, we multiply the number of vehicles going through this edge times the travel time, which in itself is a function of the number of vehicles. So this is the objective. And of course, in addition to the objective, we have constraints. The first constraint is very natural, and it arises in any application that involves some flow modeling of our system. So the first constraint is
Kiril, can I stop you just for a quick clarification question? Where does time come into account here? So the number of cars on an edge is a function of time, right? Of a specific
it's an excellent question. The model that we are assuming here is time invariance with respect to the demand. So we are thinking about a window of time in which every few seconds, for instance, arrive the same number of passengers that want to travel between a given OD pair, origin destination pair. And so it does have so once you get this, once you find a solution, it tells you within this window of time for a specific vehicle exactly what are the stops that it would take along the way and where it would get there. But the limitation of the travel time function that we're using is that it cannot account for situations in which the travel demand changes. To do that, we need to infuse into our models more realistic models of traffic flow, but this introduces a lot of complexity. And so this is why we're currently working with the time invariant setting. I hope that it answers the question.
So I have another question, since we're here. How is this convex? I mean, you have discrete decisions there, right, about which car is going to pick up which passenger.
Right. But we do have, what we're doing here is a relaxation where the variables are not necessarily whether a certain vehicle is using a certain road, but what percentage of this vehicle is using the given road. So it's a flow model. It's a relaxation of the model.
It's like the LP relaxation of a myth.
Indeed, yeah. But I would say that in the context of our problem, because we're thinking about a very system that has multiple vehicles, you can actually prove that if you have enough vehicles, you can round this linear solution to an integer solution, and you would lose very little of the approximation or the solution quality.
Yeah. Okay. Great. Thanks.
So just to wrap up this representation of the problem, we have this passenger flow constraint. We want to ensure that every passenger will leave his origin and get to its destination. In addition to that, we also have the constraint that we want to ensure that the system will get rebalanced. So what do I mean by that? Without rebalancing, we will have empty vehicles accumulating in the three leftmost vertices of the graph. Okay, so, and we want to also specify where empty vehicles would go next. What are the next passengers that they're going to pick up? Now, this constraint is a little bit more tricky to reason about because we don't know a priori where empty vehicles should end up or what are the next passengers that they should pick up. This is part of the solution. Okay, this is something that is defined by the solution that we're going to find to solve for this problem. And so now I want to walk you through the approach that we came up with to solve this problem. What we are doing here is we're using one of the most fundamental tools that we have in the entire world of math and computer science. We're using a mathematical reduction. We show that the A mode routing problem, the problem that we had in the previous slide, can be transformed into a simpler problem called traffic assignment. So what is a traffic assignment problem? It's exactly the problem that we had earlier, but without this annoying rebalancing constraint. The way you can think about this new traffic assignment problem is that you simply have a bunch of people that have their own vehicles, and you want to route those people in a way that minimizes the total travel time. Okay, but now because every person has its own vehicle, we don't need to account for rebalancing constraint. Once a person gets to its destination, it just parks its car and we don't have to worry about it anymore. Okay. So now there are two questions. First, how do we do this transformation? And this is what I'm going to show you in the next few slides. And second, why would we care about it? And I'll answer the latter questions later on. For now, let's focus on how do we actually achieve this transformation. So now we're going to describe how we transform it. What we want to do is to encode implicitly through the traffic assignment problem the rebalancing constraints of our empty vehicles. But again, the challenge is that we don't know where empty vehicles should end up, because otherwise it would be easy to do. We can just represent empty vehicles as if they were new travel demand. But we can do something similar to that. So if we are just looking at the input to this problem, we know where empty vehicles would end up. This is in the three leftmost vertices of this graph. Okay. Now the question is, where should we send them if we're representing it as a traffic assignment problem? Now the reduction that we're doing here is quite simple. We can add a new dummy vertex called the rebalancing destination node, which will be the destination node for all of those empty vehicles. And this is the input that we will give the traffic assignment problem. Now, how do we ensure that the system gets rebalanced, and what is the quality of the solution of it? So just notice here that we draw connections from each origin vertex of a passenger trip to this new rebalancing destination node. This would be this red vertex, this red edge. And just the way that we will think or interpret the solution to the traffic assignment problem would be such that if we'll take a specific empty vehicle, the passenger trip that it's going to rebalance would be simply the last vertex that appears on the road on the route to the rebalancing destination node. Okay, so now it's still unclear, how do we ensure rebalancing? How do we ensure a good quality of a solution for this traffic assignment problem? What we show in the paper is that we can optimize mathematically the values of the red edges such that we can penalize for situations in which not the correct amount of rebalancers arrive to each given origin vertex of a passenger. Moreover than that, we can show that by solving this new traffic assignment, we get a solution that is fully rebalanced, as well as it's the optimal solution to the original A mode problem. So by solving this simpler traffic assignment problem, we get an optimal solution for the A-mode problem, which we originally started with. So there's still one missing piece of the puzzle, which is why would we care about this transformation in the first place? Now, it turns out that the traffic assignment problem also has a lot of structure that we can exploit. This time we're exploiting it practically. So the traffic assignment is, again, a convex program. But there is something magical that happens when we apply a specific convex programming algorithm to this traffic assignment. So usually when we apply a gradient descent method over a convex program, we need to solve multiple linearized version of the problem. If we apply a specific Frank-Wolf algorithm, which is one of the first gradient descent algorithms for convex programming, on the traffic assignment problem, instead of solving a linear version of the problem in every step, all we need to do is to solve multiple shortest path queries. So we break, essentially by doing this transformation, we break our convex program into a sequence of shortest path queries, which we can, first of all, implement in a parallelized manner. And in addition to that, we can exploit different new approaches for shortest path queries over transportation networks, which make it even more efficient. So this is why we started with this transformation from the first place, and this is how we can scale to very large problem instances, such as the one I presented in a few slides earlier. And we're currently looking into different approaches to extend such an algorithm to more realistic problem instances. For instance, we would like to understand how to model more realistic traffic flow properties, such as having time variance and accounting for shockwave phenomena that happen in real traffic. We don't know still how to account for ride-sharing capabilities. For instance, multiple people going between not necessarily the same origin and destination, how we can couple multiple passengers from different places into the same car. We would like to understand how to account for battery capacity constraints for electric vehicles. We also currently do not account for human drivers that are found on our road. And we're only assuming that we have an entire control of all the vehicles that we have on our roads, which is unrealistic. And this is one of the areas we would like to get into more in the future. Now, the last thing that I want to mention in this context is that autonomous vehicles are going to be useful, they're going to be efficient, but still there is a limit of how much efficiency we can get from a system that consists of only autonomous vehicles. The thing is that autonomous vehicles have limited capacity, and no matter how far we will pull them, we will eventually again introduce more and more congestions. And just as an example for that, you can see that the figure we have on the left. This is actually not an illustration; it's an actual photograph that demonstrates how inefficient single capacity or small capacity vehicles are. So autonomous vehicles are useful for last mile or last 2 mile travel, but it's unavoidable to account for their interaction on a more larger scale with the public transit. So in the future work, we would like to integrate our models and systems and to reason about A-mode systems together with public transit, as well as the behavior of users on those systems. And again, I want to emphasize that this is not only a question of modeling those systems, but also how do we solve them efficiently and effectively. Now, the last point that I want to make in this talk is that considering that we have this global perspective and we have the opportunity to design the tools that will operate our future transportation systems, we can start thinking about not only optimizing for the efficiency or the cost of those systems, but also how we can use them in a way that allows to overcome the limitations or societal limitations of our current transportation system. And so we can strive for accessibility, increased fairness, and even sustainability. I'd like to very briefly mention that we had recently made some modest progress in this context, where we designed algorithmic approaches that allow us to balance between the efficiency and the fairness that we get from our transportation systems. Now, what is the interaction between efficiency and fairness? In many cases, these are two opposing objectives. For instance, if we just optimize for efficiency, we can get solutions that are highly unfair. So two people going from the same origin and destination might have vastly different travel times, which is highly unfair. And so we designed algorithmic approaches that can optimize for a given level of fairness while accounting also for the efficiency of the systems. We've also extended those ideas to account for the effect that our transportation systems have on wealth inequality, and how do we optimize wealth inequality with respect to the efficiency of our systems. So moving forward, skipped a few slides. It will be very important to understand in the future how all the different players within the transportation ecosystem come together, and how each one of them influences one another, and how we can, for instance, account for the behavior or the needs of users, the budgets of a municipality, and the greedy behavior of an operators of autonomous vehicle companies. And just to wrap up this part of the talk, the way I envision we will reason about those smart mobility systems, we will have some higher level policy that would account for the interaction between the different players. This would introduce lower level optimization problems that we need to solve, which would route people as well as vehicles and transit. And at the end, we will execute those routes from the central layer using our lower level coordination and motion planning algorithm for multi vehicles in this case. So with that, I'd like to wrap up this talk. I hope that I gave you some flavor of what kind of problems we're facing when we're dealing with multi-robot systems, and where I believe this area is going to go to in the future. I hope that I gave you some insights into how I believe, at least, as we will think about smart mobility and how it interacts with autonomous vehicles. So now I would like to thank you for your attention. I would like to thank all my collaborators that I mentioned for this talk, especially the ones who appear on this slide. And I would now take your questions. Thanks.
Thank you, Kiril. We have time for one or two very brief questions, and then we have to finish, or I won't be able to take my daughter again.
I have to go as well in 1 minute, but let me ask you this quickly. All of your approaches are centralized, right? It's unrealistic to assume you'll be able to control traffic on a citywide scale in a centralized manner. I mean, even just in terms of communication, not even the scale. So what do you think you can do in like real citywide traffic planning?
That's a really good point. I do agree that working with a completely centralized approach is unrealistic. It's also unsafe. We might have something happening in a small road segment, an accident that we want to avoid all of a sudden, and we won't be able to send the information to the main controller. So the way I think about it is there will be probably some hierarchy between the communication layers, but we still don't know how to implement those approaches in a distributed way. This is definitely something that I want to explore in the future. Yeah, and I also want to mention that the centralized approach, in a way, this gives you the best performance you can aim for, and at least some lower bound that the decentralized approach would strive to get close to. So I do think that this is a good way to start thinking about those problems.
Right. Okay, thank you.
Last question by Dean, and then we'll have to wrap things up.
Hi, Kiril. I was wondering if there are any simulation platforms related to smart mobility for multi-agent algorithms, but just like more focused on smart mobility applications. Just for example, like you have Kala and other simulations for single agent autonomous navigation. Are there anything for multi-agent systems?
Yeah. There are quite a lot of traffic simulators, and you can embed into them. You can design controllers for specific vehicles, and you can simulate it over entire city, for instance.
Can you just throw the recommended names you have? Just one interested in seeing them.
Yeah, sure. There's C-Mobility, and I can share with you a few more names afterwards.
Okay, sure. Thank you.
Sure.
Okay, thank you, Kiril, for this really broad talk. It was really nice to see how you started with a simple multi-robot motion planning systems and got to the complex interactions of fairness and path length between users and mobility on demand systems. Kiril is available if anybody wants to talk to him. And I think that concludes this session. Thank you, guys.
Thank you,
everyone. Bye-bye.
Thank you.
Thank you. Great talk.